Something reached us from before time. Scientists just detected a signal so ancient it stretches back to a moment when the universe barely existed. We are talking about a whisper from 13.8 billion years ago, and some researchers believe part of it may have started even earlier than that. Tonight, we go back, past the first stars, past the first light, past the edge of everything we thought was possible. If you enjoy this journey, subscribe and leave a like. It genuinely helps. Now steady yourself. We begin. Look up on a clear night, and you are staring into a trap. Every star, every smudge of light, every faint glow hanging in the dark is sending you a signal from the past. Light moves fast, about 5.9 trillion miles in a single year, but space is so enormous that even at that speed, light takes real time to cross it. The star you see overhead might look fine right now. The light hitting your eye left that star hundreds of years ago. The star could already be dead. You would have no way of knowing. That delay is the foundation of everything in this story. Scientists use that delay as a tool. The farther away something is, the older the light coming from it. Point a powerful telescope at a galaxy 2 billion light years away, and you are watching that galaxy as it existed 2 billion years ago. Astronomers have essentially built a time machine out of patience and lenses, but there is a wall. At a certain distance, the light simply runs out. Space has been expanding since the universe began. Light from the earliest moments has been racing toward us this entire time, but the space it needs to cross keeps stretching. Right now, the edge of what we can observe sits roughly 46 billion light years away in every direction. Past that boundary, the light from those regions has never had enough time to reach us. Those regions exist. We just cannot see them. Scientists call this the observable universe. It is like standing in the middle of a fog so thick that you can only see about 46 billion light years in any direction. Everything beyond that edge is completely invisible to us, and nothing we build on Earth will ever change that. The universe is running away from us, faster than light can follow. That might already seem impossible to wrap your head around. Hold that feeling. Now, here is what makes it stranger. Everything inside that boundary, every galaxy, every nebula, every particle of dust floating in the dark, all of it is just a sliver of what actually exists. The full universe could be hundreds of times larger, maybe thousands. Scientists genuinely do not know. What we call the observable universe is the tiny bubble we are stuck inside, peering out through our instruments, trying to understand the whole ocean from one glass of water. Inside this bubble, though, the view goes deep, very deep. When telescopes push to their absolute limits, they stop seeing galaxies and start seeing something else entirely, a faint, uniform glow, a radiation that fills the entire sky, a signal so old it predates every star that has ever burned. This glow is the cosmic microwave background, the oldest electromagnetic signal in existence, and it sits at the very edge of our observable limit. Getting there required the universe to go through something almost impossible to imagine. 380,000 years. That is how long the universe had to exist before a single ray of light could travel freely through it. Before that moment, everything was so hot and so dense that light could not move more than a few feet without being absorbed. The universe was a prison for photons. Every particle jammed together, vibrating with unimaginable heat, the whole cosmos locked in a glowing, opaque fog. Then, something changed, and when it did, the universe opened like a shutter, and light finally ran free. That moment left a scar across the entire sky, and we are still reading it today. Every time you look at something, you are already looking into the past. That sounds strange, but it is physics. Light carries information from a source to your eyes. It moves at a fixed speed. That means there is always a gap between when something happens and when you see it. When you look at a friend standing 30 feet away, you are seeing them as they were about 30 billionths of a second ago. That gap is so tiny, it feels like nothing. Stretch that gap to cosmic distances, and it becomes everything. The moon sits about 2.4 seconds away by light. When you see it, you are seeing it as it was 2.4 seconds ago. The sun is 8 light minutes away. If the sun vanished right now, we would keep orbiting a ghost star for 8 full minutes before the darkness reached us. The nearest star beyond our solar system, Proxima Centauri, sits 4.2 light years away. The light you see from it left home 4 years ago. Now, keep going. The Andromeda Galaxy, the closest large galaxy to our own Milky Way, sits 2.5 million light-years away. Every image ever taken of it shows the galaxy as it existed 2.5 million years ago, before modern humans existed on Earth. When astronomers photograph a galaxy cluster 10 billion light-years away, they are photographing the universe as it looked when Earth had not yet formed. This is why telescopes are time machines. Power does not just mean seeing farther, it means seeing older. The James Webb Space Telescope, launched in late 2021, can detect galaxies so distant their light has taken over 13 billion years to arrive. These galaxies formed when the universe was only a few 100 million years old. When Webb captures their light, it is receiving a message written before our entire solar system existed. But there is a limit. There is always a limit. Around 380,000 years after the universe began, the cosmos was still too hot and dense for light to move freely. Before that point, everything was locked in a churning plasma, a soup of charged particles so thick that photons could barely travel before being absorbed and re-emitted. No telescope can see through that wall because no light escaped it. This is called the surface of last scattering. It is the oldest thing our eyes can reach. Past it, the universe is opaque to every form of light. Any events that happened before 380,000 years in are hidden behind a curtain we cannot pull back with electromagnetic signals, except for one possibility. One type of signal that does not use light at all. Relic neutrinos, subatomic particles that broke free from the early universe just 1 second after the expansion began. They passed straight through the plasma that blocked all light. They have been traveling uninterrupted ever since, carrying information from a time before the universe was even a minute old. Catching those particles would be like finding a voice recording made in a room before anyone could see inside it. Scientists are working on detectors sensitive enough to find them. So far, no one has succeeded. The particles exist everywhere, including inside your body right now, but they interact with ordinary matter so rarely that they slip through everything we build without leaving a trace. What we can read, though, is that ancient wall of light they bumped up against. And what that wall reveals about the universe's earliest moments is even more disturbing than we expected. Somewhere in the static of an old television set, there is a message from the birth of the universe. Before digital signals took over, broadcast televisions picked up stray electromagnetic noise whenever they were not tuned to a channel. A small fraction of that static came from the cosmic microwave background, ancient light that has been traveling since the universe was 380,000 years old. It arrived in your living room, it passed through the walls, it passed through you. Right now, at this very moment, you are swimming in it. The cosmic microwave background fills the entire sky in every direction. It is not coming from one star or one galaxy. It is a glow that saturates all of space equally, a thermal echo of the moment the universe first became transparent. Scientists have mapped it in extraordinary detail using satellites, and what they found turned cosmology upside down. It looks almost perfectly smooth. When a team of scientists pointed their instruments at the full sky and measured the temperature of the cosmic microwave background, they found it sitting at just under -455 degrees Fahrenheit, just barely above the coldest temperature that can exist. And across the entire sky, the temperature varied by almost nothing. The differences between the hottest and coldest spots measured in the map are smaller than 100,000th of a degree. That smoothness is the mystery. For the temperature to be that uniform across every direction of space, all those distant regions would have had to be in contact with each other at some point. exchanging heat until they balanced out. Think of it like dropping ice into a hot drink. Given enough time, the temperature evens out across the whole glass. But the regions of the early universe that the cosmic microwave background reveals were so far apart that light could not have traveled between them in the time available. They matched anyway, perfectly. Physicists call this the horizon problem, and their leading answer to it involves a period called inflation, where the universe expanded so explosively fast in its first tiny fraction of a second that regions which started close together were flung apart before light could catch up. Before inflation, they were touching. Afterward, they were billions of light years apart. That theory is a leading explanation. It has not been proven, but buried inside the cosmic microwave background are even stranger details. Those tiny temperature variations, the almost invisible ripples in the otherwise smooth glow, are the fingerprints of the first structures in the universe. Every galaxy, every star, every planet that ever formed began as a tiny fluctuation in that ancient map. The cosmic microwave background is essentially the blueprint for everything. Every atom in your body traces back to one of those ripples. And then there are the spots that do not fit. Some regions of the cosmic microwave background are colder than they should be. A large cold spot, in particular, has puzzled scientists for decades. It sits in the southern sky, bigger across than 20 full moons lined up side by side, and its temperature dips lower than the models predict. Some researchers say it is a statistical fluke. Others think it could be evidence of something the standard model of cosmology never accounted for, something that may have pressed itself into our universe from the outside. What that something could be leads straight to one of the most unsettling ideas in modern physics. In the beginning, the universe was a wall. Go back far enough, and the cosmos was nothing like the open, dark space we live in today. Every point in existence was packed together in a state of almost unimaginable heat and density. There were no galaxies, no stars, no empty space between things. The entire observable universe was compressed into a volume smaller than a single grain of sand. The temperature was so extreme that matter as we know it could not form. Protons and electrons existed, but they could not bind together. Every time a proton reached for an electron, a photon of light came screaming in and knocked them apart. This went on for 380,000 years. In that state, light was a prisoner. A photon would travel a tiny distance, maybe the width of a few atoms, before colliding with a free electron and scattering in a random direction. Then it would do it again and again. The universe was opaque, the same way thick smoke blocks your view across a room. Everything was light, but none of it could go anywhere. Scientists call this the plasma era. The entire universe was a churning ocean of charged particles and trapped radiation. During those 380,000 years, nothing that we would recognize as space existed. You could not have floated through it and looked around. The fog would have been total and absolute. Every direction, every distance, all of it blocked by an endless wall of glowing plasma hotter than anything that exists anywhere in the universe today. Then the universe crossed a threshold. As space expanded, it cooled. Think of how a bicycle pump heats up when you compress air inside it, and then imagine running that in reverse. The expanding universe shed heat the same way expanding gas does. Gradually, over a long time, the temperature dropped to a point where something new became possible. Around -455 degrees Fahrenheit, the plasma cooled enough for electrons to slow down and stay near protons. For the first time, atoms formed. Hydrogen, the simplest element, appeared across the entire universe almost simultaneously, and the moment those atoms formed, the free electrons disappeared. The things that had been blocking the photons were gone. Light shot free in every direction at once. This moment is called recombination. In an instant stretched across thousands of years, the universe went from opaque to transparent. Every photon that had been bouncing around in the plasma suddenly had a clear path. The first light in the universe flooded outward in all directions, and it has been traveling ever since. That ancient light is the cosmic microwave background. The light that reaches us today left its source over 13 billion years ago, and it carries a direct image of that moment of release, the moment the universe first opened its eyes. But right after that moment, something unexpected happened. The light flooded out, and then it went dark. The universe entered a period of total, absolute silence that would last for hundreds of millions of years. No stars, no galaxies, no light of any kind, just cold gas, and gravity, and time. Picture the fog lifting all at once. 380,000 years of total opacity. Every photon imprisoned, every direction blocked by a wall of plasma. And then, in a cosmic blink, the curtain drops. Light runs free for the first time in history. Every photon that had been bouncing and scattering suddenly has clear space ahead of it and takes off in a straight line that it will follow essentially forever. That single moment is one of the most dramatic events in the entire history of the universe, and it happened everywhere at once. Imagine standing inside an ocean of glowing orange fog so dense you could not see your own hand. Then, in a span of time shorter than a human lifetime, the entire ocean suddenly clears. The glow does not vanish. Instead, it stretches outward in every direction, thinning and cooling as it goes, filling the entire universe with a flash of brilliant light, every corner of existence lit up in the same instant. Then, very slowly, that light began to fade. Stretched by the expanding universe, it shifted from visible light down into infrared, then into microwave radiation, then into the faint background glow that scientists map today. Right now, the snapshot of that moment is baked into the cosmic microwave background. Those tiny ripples in temperature that researchers have spent decades measuring are the shadows of sound waves that moved through the plasma before it cleared. When the plasma was still churning, pressure waves rippled through it, compressing and releasing, the same way sound moves through air. Different regions got slightly hotter or cooler depending on where those waves peaked. When the clearing happened, those temperature differences got locked in place. Every ridge and valley in that ancient temperature map became a seed. Where the plasma was slightly denser, gravity pulled matter together a little harder afterward. Over millions of years, those slightly denser spots pulled in more gas, and that gas pulled in more gas, and slowly, over an enormous span of time, the first structures of the universe began to take shape. Galaxy clusters, galaxy filaments, and the vast empty voids between them all trace their origins back to those sound waves moving through plasma more than 13 billion years ago. The structure of everything you have ever seen or ever will see was decided in the first 380,000 years. But in the immediate aftermath of that first flash of light, the universe entered a state that is genuinely hard to describe. It did not become bright and active. It became dark, completely, totally dark. The flash of the clearing faded below the range of visible light. No stars had formed yet. No new light sources existed. The hydrogen gas drifted and cooled in total darkness. Invisible dark matter spread through space. Gravity worked in silence, pulling and gathering, slowly condensing those drifting clouds into clumps. For hundreds of millions of years, nothing glowed. Scientists call this the cosmic dark ages, and it is one of the least understood periods in all of cosmic history. We have almost no direct observations of it. Our telescopes cannot see light from a period when no light existed. The only hope of studying it is through a specific, faint signal produced by hydrogen gas itself. A signal so quiet and so overwhelmed by modern noise that detecting it cleanly has eluded researchers for decades. That signal is about to become the key to unlocking the entire story. The lights went out and stayed out for 400 million years. After the first flash of ancient light streaked across the clearing universe, silence followed. Absolute silence. The plasma glow faded below visibility. No stars burned. No galaxies turned. Just cold, dark hydrogen gas hanging in the void, barely moving, barely interacting with anything. Astronomers call this the cosmic dark ages, and it is one of the strangest gaps in the story of the universe. We can describe it in outline. We know roughly when it started and roughly when it ended. But seeing directly into it is impossible because there was nothing inside it to see. No light was produced, no fire burned, no explosion lit up the dark. It ran from about 400,000 years after the universe began all the way to about 400 million years in. That is a stretch of time so long it is difficult to picture. Our entire solar system is only 4.5 billion years old. The Dark Ages lasted nearly a tenth of that, from the very beginning, in a universe that had yet to create a single star. During those hundreds of millions of years, gravity was doing its slow, patient work. The hydrogen gas that filled the universe after the clearing was spread almost evenly through space. But almost is not exactly. Those tiny temperature ripples from the plasma era meant some regions had just a little more gas than others. Gravity favored those denser spots. Gas drifted slowly toward the clumps. Clumps grew heavier. Heavier clumps pulled harder. The process built on itself in a chain of accumulation so gradual that a single step might have taken millions of years to show any visible change. And alongside the hydrogen, invisible dark matter was doing the same thing. Dark matter does not emit light, does not absorb light, and does not interact with ordinary matter in any way that scientists have directly detected. But it has gravity. During the Dark Ages, it was the skeleton. It gathered first, forming an invisible web of filaments stretching across space. The ordinary hydrogen gas fell into those filaments, like sand settling into cracks in a sidewalk. The dark matter carved the channels and the gas followed. You would have floated through that universe and seen nothing, pure black in every direction. No horizon, no glow, no landmark. Just the faint warmth of the cosmic microwave background radiation pressing against you from all sides, invisible and untouchable, cooling by fractions of a degree every million years. Even the concept of night sky did not apply. There was no sky to speak of. There was only the dark. What makes this period so important to researchers is that everything that came after, every galaxy, every star, every atom fused in a stellar core, grew from the structure that formed during the Dark Ages. The arrangement of the modern universe was set during those quiet hundreds of millions of years. The seeds were planted in darkness, and the harvest was the cosmos we live in today. But to study those seeds, scientists needed a signal, something that hydrogen gas itself produces even when no star is shining. They found one. And it comes from a place as small and quiet as a spinning electron. The story of that signal and the desperate search to hear it clearly is stranger than most people expect. In the dark, the universe had a skeleton. During the cosmic Dark Ages, two things shared the entire cosmos. Cold hydrogen gas, the simplest substance in existence, made of one proton and one electron bonded together, and dark matter, something whose identity scientists still cannot fully explain. These two ingredients filled all of space in different ways. The hydrogen was the visible component, at least in theory. It had mass, it had structure, and under the right conditions, it could eventually radiate a detectable signal. The dark matter was something else entirely. It left no fingerprints on any detector. It passed through everything. It emitted nothing. It absorbed nothing. Scientists discovered dark matter exists because gravity told them so. In the 1970s, astronomer Vera Rubin was studying how galaxies spin. Galaxies rotate, and the speed at which stars on the outer edges orbit the center should slow down the farther out you go, the same way outer planets in our solar system move more slowly than inner ones. But Rubin found that the outer stars and galaxies were moving far too fast. The math said they should be flying off into space. Something unseen was holding them in, something providing extra gravitational pull without revealing itself through any kind of light. Whatever it is, it outweighs all the normal matter in the universe by a ratio of roughly 5-to-1. For every pound of atoms in the cosmos, there are 5 pounds of dark matter. During the cosmic Dark Ages, this invisible majority was the dominant force shaping space. Dark matter clumped first. Because it did not interact with light or heat, it could cool and cluster without the resistance that slowed ordinary matter down. It assembled into enormous filaments and sheets, a web of invisible structure spread across billions of light years. Cosmologists call this the cosmic web, and while you cannot see it directly, its shape is stamped onto the distribution of every galaxy that exists today. The hydrogen gas followed the dark matter's gravity like water following a riverbed. It fell into the grooves carved by the dark web, gathering in filaments, pooling in nodes where the filaments crossed. The denser regions became the nurseries, where, eventually, stars would ignite. Inside those nurseries, the hydrogen was extraordinarily cold. Temperatures dropped to a few dozen degrees above absolute zero. The atoms moved slowly, interacting rarely, drifting in enormous clouds that stretched across distances measured in thousands of light years. A single cloud could contain enough gas to build millions of stars. Nothing was burning yet, but the conditions were building. As gravity compressed the densest pockets of gas, heat slowly built up at their cores. Pressure rose. The atoms were squeezed tighter and tighter, a process that moved at a pace humans cannot perceive but was nonetheless relentless. Across the dark universe, hundreds of thousands of these compression zones were developing simultaneously, each one a future star, decades of millions of years away from crossing the threshold that would make it shine. What comes next, when those first ignitions finally happen, changes the universe in a way that no event since has matched. But before we get there is a quieter story happening inside those drifting hydrogen clouds. A tiny signal, produced without any star, without any explosion, just from the nature of the atom itself. And it holds a record of the entire Dark Age. Gravity never stops. During the cosmic Dark Ages, it was the only thing doing anything. No light, no heat, no nuclear reactions. Just the slow, constant pull of mass toward mass, working across hundreds of millions of years with absolute patience. The hydrogen gas and dark matter left over after the universe cleared were almost perfectly spread out. Almost. Those tiny temperature ripples from the plasma era had left some regions slightly denser than others. In human terms, the difference was insignificant. In cosmic terms, it was everything. Gravity does not care about significance. It cares about mass. A region with even a fraction more gas than its surroundings pulls on nearby material with a fraction more force. More material drifts in. The region grows denser. The pull increases. The drift accelerates. The process builds on itself through a feedback loop that, given enough time, can turn the faintest whisper of a density difference into a structure the size of a galaxy cluster. Scientists call this process gravitational collapse, and it is the engine behind everything that exists in the modern universe. To understand the scale, picture a perfectly still swimming pool. Now, add one extra drop of water to a spot near the center. The surface tension and weight of that tiny drop creates an infinitesimally small depression. Water at the surface tilts toward it, barely, invisibly, by a millionth of a degree. But in a universe with hundreds of millions of years to work and no resistance to slow it down, that tilt compounds into a flow, and the flow compounds into a current, and the current deepens the depression until it becomes a drain that pulls in everything around it. That is how the cosmic web was built. The dark matter collapsed fastest because nothing slowed it down. Light pressure and heat, which resisted the compression of normal matter, had no effect on dark matter. It fell into its own gravity wells freely, assembling the skeleton of the cosmic web before the hydrogen gas could keep up. The dark matter halos that formed during this period became the scaffolding that ordinary matter later fell into. By the time the Dark Ages were halfway through, the invisible architecture of the universe was largely in place. The web of dark matter filaments spanned billions of light years, with dense nodes where multiple filaments crossed. These nodes marked the future addresses of galaxy clusters. The hydrogen gas, meanwhile, was pooling into those dark matter halos. As it collected and compressed, it began to behave differently. Dense pockets within the larger clouds became gravitationally unstable, meaning the pressure trying to push them outward was no longer strong enough to resist the gravity pulling them inward. These pockets began their long collapse toward the densities required for nuclear fusion. Each collapsing pocket was a star in waiting, but before the first one crossed the line, before the first nuclear fire lit in the dark, one more process was happening inside all that cold hydrogen. Something so small it is easy to miss. A flip of a single electron, a tiny burst of radio energy released into the void. That tiny signal, multiplied across trillions of hydrogen atoms, across billions of light years of gas, became the most important broadcast in the history of the cosmos. It is still reaching us today, faint and stretched, from before the first star ever burned. Deep in the dark, hydrogen was talking. Every atom of hydrogen in the universe is made of the same two parts, one proton at the center and one electron orbiting around it. The proton and the electron each have a property called spin, which you can picture as a tiny magnetic arrow pointing either up or down. Most of the time, the proton and the electron in a hydrogen atom have their spins pointing in opposite directions. Sometimes they flip to point the same way, and when the electron flips back from matching the proton to opposing it, something happens. It releases energy, a single, precise photon with a wavelength of exactly 21 centimeters, roughly the length of a school ruler. This happens rarely. For any single hydrogen atom, the average wait between flips is about 11 million years, but space contains an enormous number of hydrogen atoms. During the cosmic dark ages, there were enough hydrogen atoms spread across the universe that even at one flip per 11 million years per atom, the combined output was a steady, continuous radio signal radiating across the entire cosmos. A faint hum produced by trillions upon trillions of tiny magnetic flips happening constantly in the dark. This signal is called the 21 centimeter line, and it is the only direct window into the dark ages that exists. By mapping where this signal comes from and at what frequencies, scientists can trace the distribution of hydrogen gas across billions of light years and billions of years in time. A frequency that has been stretched by the expansion of the universe tells researchers not just where the hydrogen is, but when in cosmic history it was emitting. Low frequency means old signal. High frequency means newer. By scanning the full range of frequencies, researchers can build a three-dimensional picture of how hydrogen filled the universe from the dark ages all the way through the first galaxies forming. This technique is called intensity mapping, and it is one of the most ambitious projects in modern astrophysics. The signal itself is extraordinary. The 21 centimeter line has stayed at precisely the same frequency since it first appeared in the early universe. The hydrogen atoms emitting it today are physically identical to the hydrogen atoms emitting it 13 billion years ago. They have not changed. They are the oldest unchanged substance in existence, and they carry a record of everything the universe looked like before a single star burned. But actually, capturing this signal cleanly is a problem on an almost absurd scale. The 21 centimeter line coming from the ancient universe arrives at Earth so faint and so stretched that it sits in the same frequency range as radio broadcasts, phone towers, and airplane navigation systems. The modern world is drowning it out. Separating the ancient cosmic whisper from the noise of human civilization is like trying to hear a single person whispering from across the country while standing in the middle of a rock concert. To even attempt it, scientists had to get creative. They built their telescopes somewhere the noise could not reach them, and even that was not enough. Radio noise is everywhere. Pick any spot on Earth, and there are signals flying through the air. Phone calls, navigation beacons, satellite data, broadcast radio, Wi-Fi, radar systems. The electromagnetic spectrum from ground level is dense with human transmissions, layered on top of one another at frequencies spanning the entire range that radio telescopes need to study. The 21 centimeter hydrogen signal from the dark ages arrives at Earth after traveling for over 13 billion years. By the time it gets here, it has been stretched to lower frequencies and diluted to an almost unimaginable faintness. It is real, it is present, but it is buried. Separating it from man-made radio interference is one of the most technically demanding problems in modern science. The first solution was geography. Radio telescopes built to study the ancient hydrogen signal are placed as far from cities, roads, airports, and power lines as physically possible. Teams have built facilities in the Karoo Desert in South Africa, the remote outback of Western Australia, and the high-altitude plateaus of Chile. These sites were chosen specifically because human activity is minimal and the atmosphere is dry, which helps because water vapor absorbs radio waves and adds its own layer of noise. Even in those locations, complete silence is impossible. Satellites pass overhead constantly. Aviation transponders chirp. Distant cities leak signals over the horizon. Researchers have had to design algorithms that identify and remove man-made interference in real time, essentially teaching their computers to recognize and discard anything that looks like it was made by humans rather than hydrogen. The Hydrogen Epoch of Reionization Array in South Africa and the Murchison Wide Field Array in Australia represent some of the most sophisticated attempts to hear this signal. Both facilities consist of hundreds of individual antenna elements spread across miles of desert, working together as a single enormous telescope. The larger the collection area, the more sensitive the instrument, and sensitivity is everything when hunting for a signal this faint. Still, results have been frustratingly incomplete. Researchers have managed to put limits on what the signal should look like. They have made statistical detections that strongly suggest the signal is there, but a clean, confirmed detection of the hydrogen signal from the actual dark ages remains one of the outstanding goals of observational cosmology. The noise problem on Earth may simply be unsolvable, which is why a growing number of scientists have stopped looking at deserts entirely and started looking up. The far side of the Moon is the quietest radio environment in the entire solar system. The Moon's own body blocks every transmission from Earth. No satellites, no phone towers, no airport radar, nothing. The lunar surface on the far side experiences radio silence that is orders of magnitude deeper than anything achievable on Earth. Several space agencies and private organizations have proposed lunar radio telescope arrays that would sit permanently on the far side of the Moon, pointing outward into deep space. The technical challenges are enormous. Building and maintaining a network of antennas on the Moon requires robotic construction, power systems that survive 2 week lunar nights, and data relay systems that communicate around the Moon's edge. The science waiting on the other side of those challenges may be the deepest look into cosmic history ever achieved. But detecting the 21-centimeter signal from space requires understanding exactly what that signal should look like at its cleanest. And one key to that comes not from radio waves at all, but from something almost impossible to catch. The Moon has been orbiting Earth for 4.5 billion years, and scientists only recently realized it is the perfect telescope. The Moon's far side never faces Earth. It is permanently turned away from every city, every satellite, every radio tower on the planet. When astronauts from the Apollo program orbited around behind the Moon, their communication systems cut off completely. No signals reached them. No signals escaped. For the duration of that transit, they were in the most communication-isolated spot any human has ever occupied. That isolation is exactly what radio astronomers need. The electromagnetic noise from Earth's civilization reaches the near side of the Moon constantly. Radio signals from our planet carry far into space, and the Moon's near side sits directly in the path of that broadcast. Any telescope placed there would face the same interference problem as Earth-based observatories, just from a higher vantage point. The far side is different. The body of the Moon, 2,100 miles thick, sits between any antenna on the far side and every human-made transmission on Earth. The shielding is physical, massive, and absolute. The radio silence there is so complete that scientists describe it as the quietest location in the entire inner solar system. For the 21-centimeter hydrogen signal from the Dark Ages, this matters enormously. That signal has been stretched by the expansion of the universe into a low frequency range that overlaps almost perfectly with human radio communication. On Earth, filtering out the interference requires enormous computing power and still leaves uncertainty in the results. On the far side of the Moon, the interference does not exist. Several serious proposals have been made. NASA has studied the concept of the Lunar Crater Radio Telescope, a design that would use a natural crater on the far side to support a wire mesh antenna, similar to the massive dish at Arecibo in Puerto Rico, but even larger. The crater walls would provide structural support, the mesh would collect radio waves, and the natural bowl shape would focus them toward a central receiver. Other proposals involve flat antenna arrays deployed by robots across the lunar surface. Rather than one large dish, these designs distribute hundreds of smaller receivers across miles of terrain, working together the same way the desert arrays on Earth do. The engineering problems are real. The Moon experiences temperature swings of 600 degrees between its sunlit and shadowed periods. Equipment must survive 2 weeks of freezing darkness, followed by 2 weeks of intense radiation. Power systems must operate independently. Data must be transmitted back to Earth via relay satellites stationed at points where the Moon's edge does not block the signal. Robotic construction technology is advancing rapidly. Missions to the lunar far side have already landed, including the Chinese lander that became the first spacecraft to touch down on that terrain. The infrastructure knowledge is building. If a functional radio telescope array reaches the far side of the Moon, the science it could deliver would be extraordinary. A clean detection of the Dark Ages hydrogen signal would give cosmologists their first direct observational data from the most unexplored period in cosmic history. But there is another signal from even earlier in time, one that passed through the Dark Ages without leaving a trace, that researchers are hunting with different tools entirely. 1 second after the universe began, something escaped. Light was still trapped. The plasma that would hold photons prisoner for 380,000 years had barely formed. The universe was an unimaginably dense, unimaginably hot ball of churning particles, hotter than anything that exists today by many orders of magnitude. And in that first second, before the universe was old enough to have a name for itself, a type of particle decoupled from everything else and began traveling freely. Neutrinos. Neutrinos are subatomic particles with almost no mass, no electric charge, and an almost supernatural ability to avoid interacting with other matter. They are produced by the trillions in the cores of stars, by nuclear reactions, by the radioactive decay of atoms. Right now, about 65 billion of them are passing through every square inch of your skin every second, coming from the sun alone. You cannot feel them. Nothing can stop them. They pass through Earth as if it is not there. In the first second of the universe, conditions were so extreme that even neutrinos were interacting with other particles constantly. The density was so high that everything was in contact with everything else, and the neutrinos were trapped in that primordial soup along with everything else. Then the universe expanded enough that the density dropped below a critical threshold. The neutrinos stopped interacting. They decoupled from the rest of the matter and radiation in the cosmos and began traveling freely, carrying a snapshot of the universe exactly as it was at that 1 second mark. Scientists call this the cosmic neutrino background, the particle equivalent of the cosmic microwave background, but from a time that predates it by 379,999 years. Every second of every day, an ocean of these relic particles washes over Earth. They carry direct information from a moment just 1 second into the history of the universe. They have been traveling since before the sun, before Earth, before the first star, before anything we can see existed, and no one has ever directly detected a single one of them. The challenge is the same property that makes them so valuable as messengers. They almost never interact with anything. Detectors capable of catching solar neutrinos require enormous tanks of liquid buried deep underground, shielded from cosmic rays, filled with hundreds of tons of dense fluid, and even then, they only register a handful of interactions per day. Relic neutrinos carry less energy than solar neutrinos, making them even harder to detect by orders of magnitude. Current estimates suggest that catching a single relic neutrino interaction in a detector the size of a city block would take thousands of years. Physicists have proposed next-generation detector designs, including materials like superfluid helium, that might respond to the tiny energy transfer of a relic neutrino interaction. The physics are sound. The engineering does not yet exist at the required scale, but the particles are there, 300 of them, right now, in every cubic centimeter of space around you, inside you, passing through you without a greeting. They hold a record of the universe before any light could move, before any atom existed, before the first second of history had finished passing. And what happened in that very first second is stranger than the Dark Ages, stranger than the first stars, stranger than almost anything that comes after. Your body is full of ghosts from the beginning of time. Take any cubic centimeter of space around you. That is a volume roughly the size of a sugar cube. Inside that cube, right now, sit approximately 300 relic neutrinos. They are relics from the universe's first second, produced in the extreme heat of the earliest moments and traveling freely ever since. They pass through the walls of buildings, through the entire thickness of the planet, through every material humans have ever made, without slowing down or leaving a mark. You are not touching them. They are not touching you. They exist in the same space as you, but the interaction between them and your atoms is so rare that your entire body, over your entire lifetime, will absorb essentially none of them. The reason comes down to forces. Matter interacts through four fundamental forces: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Most of what you experience daily involves electromagnetism, the force that governs how atoms bond, how light behaves, and how your fingers feel a surface. Neutrinos only respond to gravity and the weak nuclear force. Gravity is far too faint to matter at subatomic scales. The weak force only operates at distances shorter than a proton's diameter. For a neutrino to interact with an atom, it needs to pass within an unimaginably small distance of the nucleus of that atom. Given the vast emptiness inside every atom, even solid objects like stone and steel are, from a neutrino's perspective, almost entirely empty space. A neutrino passing through a block of lead 1 light-year thick would have only a 50% chance of hitting anything at all. This makes them extraordinary as messengers, and essentially impossible as targets. The 300 relic neutrinos per cubic centimeter are spread through the entire universe at that same density, everywhere. In the vacuum of space between galaxies, inside stars, inside planetary cores, inside every living thing on Earth. They have been everywhere since the first second, and they will stay everywhere essentially forever. What makes this staggering from a scientific perspective is the information they carry. Those particles last interacted with the rest of the universe when it was 1 second old. They carry an imprint of the density and temperature of the cosmos at that moment. Detecting them would be like reading a photograph taken before the universe had formed so much as a single atom. The information encoded in relic neutrinos would tell scientists about the universe at energies and densities that no human-made particle accelerator can recreate. It would test physics beyond what any telescope can reach. It would push observational science to within 1 second of the beginning of everything. Several physics teams are working toward detectors that might accomplish this within the coming decades. The designs involve capturing the tiny recoil that a neutrino produces when it passes close enough to a nucleus to exert a faint gravitational or weak force nudge. The energy involved is so small that the detectors must be cooled to within fractions of a degree of absolute zero and shielded so completely from vibration that even footsteps nearby would contaminate results. The challenge is real. The reward is a direct measurement from the universe's first heartbeat, but to understand what the universe was doing at that moment, it helps to see what came next. The first time anything exploded. Catching a neutrino, is like trying to catch fog with a net made of fog. The particle exists. The physics confirms it. The math predicts everything about it. And yet, for most of human history, the neutrino was a theoretical object, something that had to exist based on the equations of particle physics, but had never been directly seen. Scientists had to build some of the most extreme environments ever created just to verify that neutrinos are real. The first confirmed detection happened in 1956. Two physicists, Clyde Cowan and Frederick Reines, placed a tank of liquid next to a nuclear reactor. Nuclear reactors produce enormous numbers of antineutrinos as a byproduct of fission. By placing the detector close enough to the reactor and waiting long enough, they hoped to catch a handful of the antineutrinos interacting with hydrogen nuclei inside the liquid. After months of operation, they observed flashes of light corresponding to exactly the interaction they predicted. The neutrino was real. They won the Nobel Prize 40 years later, but those were reactor neutrinos, produced by nearby machines and arriving in massive numbers. The relic neutrinos from the first second of the universe carry far less energy, and no reactor in existence produces anything comparable. The detection challenge for relic neutrinos is so much harder that it sits in a completely different category. Modern neutrino detectors are buried deep underground because the rock above them acts as a shield, filtering out cosmic rays and other particles that would otherwise trigger false signals. The most famous is the Super Kamiokande detector in Japan, a stainless steel tank, 50 feet across and over 100 feet tall, filled with 50,000 tons of ultra-pure water. Lining the walls are over 11,000 light sensors, waiting for the rare flash of light produced when a neutrino strikes a water molecule. That detector registers roughly 3 solar neutrino interactions per day. Relic neutrinos carry roughly 1 million times less energy than solar neutrinos. To detect them at the same rate, you would need a detector 1 million times more sensitive, or 1 million times larger, or wait 1 million times longer. None of those options are currently achievable. The detector that could catch a relic neutrino at a meaningful rate would need to be the size of a small city, cooled to near absolute zero, and shielded more completely than anything humans have ever built. Physicists are exploring materials that might provide a path forward. Certain superconducting metals can register energy depositions so small they approach the quantum limit of what physics allows to be measured. Prototype detectors using these materials have already detected heat pulses from solar and reactor neutrinos at scales previously considered impossible. The science is advancing. The engineering is the bottleneck. Meanwhile, the particles themselves keep passing through everything, carrying their ancient information, completely indifferent to the effort being made to catch them. But while the hunt for relic neutrinos continues across the frontier of physics, 400 million years into the universe's history, the dark ended. Not quietly. The first star that ever burned would have terrified you. Go back 400 million years after the universe began. The Dark Ages are ending. Deep inside the densest pockets of cold hydrogen gas, gravity has been compressing matter for hundreds of millions of years without interruption. The cores of these collapsing gas clouds have reached temperatures and pressures that no longer exist anywhere in the universe today. The hydrogen atoms are no longer just touching each other. They are being forced together with enough energy to fuse. Nuclear fusion ignites. And for the first time since the universe went dark, something shined. These first stars, which scientists call population 3 stars, were monsters, because the gas that formed them was pure hydrogen and helium, with none of the heavier elements produced by previous stellar generations. The gas clouds they formed from collapsed much more efficiently than modern star-forming clouds do. Without heavier elements to radiate heat away, the cores heated up to extreme temperatures. At those temperatures, fusion burned harder and faster. The stars that resulted were enormous. The smallest were probably 10 to 20 times the mass of our Sun. Many were likely hundreds of times more massive. Stars at that scale are not like the steady, yellow star we orbit. They burn with a ferocity that cannot sustain itself. The energy output is so enormous that radiation pressure from the interior pushes outward against gravity with almost equal force, making the entire structure inherently unstable. To picture the size, our Sun is about 865,000 miles across. A star 300 times more massive would have a diameter large enough to swallow the entire orbit of Earth with room to spare. Now imagine one of those going unstable. These population 3 stars burn through their fuel in a fraction of the time a star like our Sun takes. Our Sun has enough hydrogen to burn for about 10 billion years total. A star 100 times more massive burns through the equivalent fuel in under 1 million years. Some of the earliest, most massive stars may have lived for only 100,000 years before their cores collapsed. 100,000 years sounds long in human terms. In cosmic terms, it is a brief flash. When they died, they did not go quietly. Stars above a certain mass threshold do not leave behind gentle remnants. They collapse so violently that the implosion reverses into an explosion of almost incomprehensible energy. The outer layers of the star are blasted outward at a fraction of the speed of light. In some cases, the core collapses directly into a black hole, and jets of plasma and radiation fire outward from the poles at nearly the speed of light. This is a gamma-ray burst. And the first ones in history happened as these earliest stars died hundreds of millions of years after the universe began. The light from those explosions carried something beyond energy. It carried the raw ingredients for everything that came after. When the first stars died, they gave everything away. The universe that existed before the first stellar generation was chemically simple. Hydrogen, helium, tiny traces of lithium. That was it. The entire periodic table, every element heavier than those 3, did not exist anywhere in the cosmos. There was no oxygen for water, no carbon for organic chemistry, no iron for planetary cores, no calcium for bones. Everything that makes complex matter possible, including the atoms inside every living thing on Earth, had to be created somewhere. That somewhere was the interior of stars. Inside the core of a large star, nuclear fusion does not just burn hydrogen. As the star ages and hydrogen in the core runs out, the fusion process advances to heavier elements. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen. The process steps up through the periodic table, each stage requiring higher temperatures and pressures than the last, each stage producing heavier nuclei that sink toward the center as a new shell of fusion ignites around them. By the time a massive star reaches the end of its life, its interior looks like a layered onion. The outermost shell still burns hydrogen. Below that, helium fusion, then carbon, then oxygen, then neon, then silicon. At the very core, iron. Iron is the endpoint because fusing iron requires more energy than it produces. When an iron core forms, fusion in the center stops, and gravity immediately wins. The core collapses in less than a second. The material that was supporting the outer layers of the star disappears, and those layers fall inward at a quarter of the speed of light. They hit the collapsed core and bounce. The resulting shockwave tears the star apart and fires the contents of all those fusion shells outward into space at enormous velocities. Every layer, carrying the atoms forged through millions of years of nuclear burning, gets scattered across the surrounding interstellar medium. Oxygen, carbon, silicon, sulfur, iron, and dozens of other elements seed the gas clouds nearby. The next generation of stars that forms in those enriched clouds will contain all those elements, and the planets that form around them will too. The first population 3 stars exploded and seeded the universe with the building blocks of chemistry. Everything that followed, every second generation star, every rocky planet, every ocean, every living cell, incorporated atoms from those first explosions. The iron in your blood was forged in the core of a star that lived and died long before our solar system formed. The oxygen in each breath you take was scattered into space by a stellar explosion billions of years ago. You are made of recycled stardust, and the recycling process started with those first monsters burning and dying in the early universe. But the deaths of the first stars did more than enrich the gas clouds. They also released the most powerful electromagnetic events in the universe, bursts of gamma radiation so intense they could be detected across nearly the full span of cosmic history. And when instruments pointed back toward those first explosions, they found something that was not supposed to exist. 10 seconds. That is all it takes. In 10 seconds, a gamma ray burst releases more energy than our sun will produce over its entire 10 billion year life. A single explosion, lasting roughly as long as it takes you to count to 10, outshines entire galaxies by a factor of millions. For that brief window, one dying star blazes brighter than everything in the observable universe combined. These are the loudest events in the cosmos, and the first ones happened when the universe was barely getting started. Gamma ray bursts occur when the most massive stars die. When a star with a mass more than 20 times our sun collapses, the outer layers fall inward so fast that the rebound explosion cannot escape spherically. Instead, the energy concentrates into two narrow jets, firing outward from the poles of the collapsing star at nearly the speed of light. These jets punch through the stellar material and blast into surrounding space, carrying an enormous burst of gamma radiation, the highest energy form of light. The jets are focused, which is both what makes them so powerful and why we can detect them from across the universe. If Earth happens to sit roughly in the path of one of those jets, the burst arrives with full intensity. If we are off to the side, we see nothing at all. Scientists estimate that for every gamma ray burst we detect, hundreds of others happen in other directions we miss entirely. In recent years, space telescopes have pushed detection back to earlier and earlier times. The current record sits at 730 million years after the universe began. A massive star formed in those ancient times burned through its fuel in less than a million years, and then detonated in an explosion whose light has been traveling toward us ever since. That burst arrived at Earth, carrying information about the environment it passed through. As those gamma rays streamed across billions of light years, they passed through gas clouds, through galaxy clusters, through the intergalactic medium. Different elements absorb specific frequencies of light, leaving gaps in the spectrum like a fingerprint. By reading those gaps, astronomers can map what the universe looked like along that entire line of sight. From the moment of the explosion to the moment of detection, the results showed something that surprised researchers. The universe at 730 million years old already had heavy elements present in detectable quantities. That means the first generation of massive stars had already lived and died, already seeded the surrounding gas with carbon and oxygen and heavier atoms, all within the first 700 million years. The cosmic dawn was happening faster than the models predicted. Each new detection pushed the timeline further back. Each burst revealed a universe that was building structure earlier, forming stars sooner, and distributing chemical complexity more rapidly than anyone expected. The standard picture of cosmic evolution was being revised with every new explosion detected. But these gamma-ray bursts, as extreme as they are, represent the end of the Dark Ages from one perspective. They mark the deaths of the first stars, the moment when the universe went from a place of silence to a place of fire. What happened between those first ignitions and those first explosions, and what the blasts did to the gas surrounding them, changed the structure of the cosmos in a way that is still visible in the sky today. And it started quietly, with light chewing through a fog. The universe was rewriting itself, and a dying star sent us the proof. When that gamma ray burst from 730 million years after the universe began finally reached Earth's detectors, astronomers did not just see an explosion, they saw a message written in missing light. As those gamma rays traveled across billions of light years, they passed through clouds of gas, through the space between galaxies, through every structure that existed along that ancient line of sight. Each type of atom they encountered absorbed a specific frequency. By the time the burst arrived, its spectrum was riddled with gaps. Each gap a chemical fingerprint left by something the light passed through. Reading those gaps told scientists what the universe contained along that entire cosmic corridor, from the explosion site all the way to Earth. The answer was not what anyone expected. Heavy elements were already present. Carbon, oxygen, silicon, atoms that require an entire stellar lifetime to forge, were detectable in the gas surrounding that ancient explosion. For those elements to exist 730 million years after the universe began, an entire generation of massive stars had already been born, burned, and died before that burst even happened. The universe had already completed one full cycle of stellar evolution, from gas cloud to nuclear furnace to explosion, in under 700 million years. That is faster than most models predicted. Cosmologists had assumed the first stars took longer to form and longer to die. The burst forced a revision. The universe had been building structure at a pace that the standard timeline underestimated. Every subsequent detection has pushed the story further. With each ancient burst caught by space telescopes, astronomers are mapping the chemical state of the universe at earlier and earlier times. They are essentially reading a history book written in light, where each chapter covers a different era and each burst provides a page. The bursts also revealed something about the medium they traveled through. In the early universe, after the first stars ignited, those stars pumped out intense ultraviolet radiation. That radiation struck the surrounding hydrogen gas and stripped the electrons away from the atoms, a process called reionization. The hydrogen, which had been neutral and relatively transparent to certain wavelengths since the Dark Ages ended, began turning back into plasma, a different kind of plasma than before, thinner and more scattered, but still capable of absorbing specific frequencies of light. The ancient gamma-ray bursts passed through regions of the universe at different stages of this reionization process. By measuring how much of their spectrum was absorbed, researchers could track how far reionization had progressed at different points in time. The cosmic dawn was not a single moment. It was a process. The universe lit up region by region, cluster by cluster, as the radiation from the first stars and the first quasars slowly ate through the surrounding neutral gas. Some regions cleared early, some stayed neutral for longer. The full transition from dark ages to a fully transparent universe took several 100 million years. That transition set the stage for everything that followed. Galaxies could now form and grow without their raw material being locked in neutral gas halos. The paths between structures opened up. The universe became navigable by light in a way it had never been before. But hidden in the map of that transition are anomalies. Temperature patterns that do not fit the standard picture. Signals that arrive from directions where the models say nothing unusual should be happening. Some of them may have a very different explanation. The universe had a second clearing, and it took 300 million years. After the Dark Ages ended and the first stars ignited, the cosmos entered a tug-of-war between light and gas. The first massive stars blazed with intense ultraviolet radiation, far more powerful per unit of mass than any stars that exist today. That radiation fired outward in every direction, and when it struck the neutral hydrogen gas filling the space between stars and galaxies, something dramatic happened. Ultraviolet light carries enough energy to knock the electron clean off a hydrogen atom. The atom, previously neutral and relatively invisible to certain wavelengths, becomes a free proton and a free electron again, the same state it was in during the plasma era, though far colder and far less dense. This process is called ionization, and the period when the first stars drove it across the entire universe is called the epoch of reionization. Picture it this way. The first stars were like torches lit inside a smoke-filled room. Each torch burned a small, clear bubble around itself. At first, the bubbles were isolated, separate islands of transparent space surrounded by walls of neutral gas. As more stars formed and more torches lit, the bubbles grew. Eventually, neighboring bubbles touched, then merged. Then the merged regions touched others and merged again. Over hundreds of millions of years, the clear regions spread until they connected into a network covering the entire universe. By about 1 billion years after the universe began, the process was largely complete. The intergalactic medium, the thin gas between galaxies, had shifted from neutral to ionized across most of the cosmos. The universe became transparent in a way it had never been since the original clearing after recombination. Telescopes can see the evidence of this transition in the spectra of ancient quasars. Quasars are the extremely bright cores of early galaxies, powered by supermassive black holes consuming matter at enormous rates. They are bright enough to be seen across almost the full span of observable space. When astronomers study the light from quasars at different distances, they can see how much neutral hydrogen the light passed through on its journey. Quasars seen from before 1 billion years show heavy absorption. The neutral gas was still thick. Quasars from after that period show much clearer spectra. The fog was gone. The epoch of reionization was confirmed. The cosmic dawn had a timeline, but what researchers found at the edges of this transition was unexpected. Some regions of the universe reionized earlier than others, and those early clearing regions aligned with areas where the density of matter was slightly higher. The parts of the universe that had more mass cleared first because they formed more stars first. The seed structure from those ancient plasma-era ripples had shaped not just where galaxies formed, but how quickly the universe became transparent. Everything connects. The ripples in plasma from 13 billion years ago controlled which regions lit up first during the cosmic dawn, and the map of those ripples is still sitting in the cosmic microwave background, waiting for every measurement to be taken. But some features in that map have no explanation in this story. Something in the oldest map of the universe does not belong. When scientists first created a detailed temperature map of the cosmic microwave background, they expected small variations, the ripples from the plasma era that seeded all later structure. Those ripples were there. They matched the predictions of the standard model of cosmology to extraordinary precision. Then they looked more carefully. In the southern sky, there is a region of the cosmic microwave background that is measurably colder than its surroundings. Significantly colder. The temperature dip is small in absolute terms, but relative to the expected variation, it stands out. The cold spot spans a patch of sky larger than 20 full moons lined up side by side. It sits there, consistent across multiple independent measurements and multiple satellite missions, refusing to average away. Astronomers call it the cold spot. Several explanations exist, and none of them fully satisfy. The first and most statistically safe answer is that it is a coincidence. In any large dataset with random variation, extreme outliers appear by chance. Flip a coin enough times and you will get a run of 30 heads in a row eventually. The cold spot might be the cosmic equivalent of a statistical fluke, a region that happened to be slightly colder and happened to be large enough to notice. But the cold spot is large, unusually large. The probability of it appearing by chance in the standard model has been calculated repeatedly, and while the numbers are not impossible, they are uncomfortable. Researchers keep coming back to it. A second explanation involves a supervoid. Voids are regions of space with significantly less matter than average. As light passes through a void, it loses a tiny amount of energy because the gravitational landscape it traverses changes while it is crossing. In a universe with dark energy driving expansion, this energy loss does not recover. A large enough void along the line of sight to the cold spot could account for part of its temperature dip. Scientists searched for such a void. They found one. A large, underdense region sits roughly 3 billion light-years away, roughly in the direction of the cold spot. It is called the Eridanus supervoid, and it is genuinely enormous, close to 1 billion light-years across. But when researchers calculated how much of the cold spot's temperature drop the void could explain, the void accounted for only a fraction of it. Something else is responsible for the rest. A third explanation has been raised and debated for years. Some theoretical physicists have proposed that the cold spot could be evidence of a collision between our universe and another universe. In certain models of cosmology, our universe is one of many expanding bubbles in a larger space. If two such bubbles collided early in their histories, the collision could have left a temperature imprint in the cosmic microwave background, a scar from an impact with something beyond our observable universe. That idea is in the category of serious scientific proposals, examined using mathematics and compared against data. It is also wildly difficult to test and has not been confirmed by any direct evidence. What the cold spot tells us with certainty is that the standard model of cosmology still has gaps, and the biggest gap of all sits at the very beginning. A scar in the oldest light is hard to explain away. The cold spot in the cosmic microwave background has now been measured independently by two separate satellite missions, the Wilkinson Microwave Anisotropy Probe and the Planck satellite. Both missions mapped the entire microwave sky with different instruments, different calibrations, and different teams of scientists. Both found the cold spot in the same place with the same characteristics. It is real. The question is what caused it? And the honest answer is that scientists genuinely do not know. The supervoid explanation accounts for some of the temperature drop. The statistics of random chance can account for some of the rest, if you are willing to accept that our particular patch of the universe happened to roll an unlikely number. Many cosmologists park it there and move on, not because they are satisfied, but because they have nothing better to replace it with. A smaller group of researchers takes the anomaly more seriously. They point out that the cold spot is not the only unusual feature in the cosmic microwave background. There is also the hemispherical asymmetry, a pattern where one half of the sky has slightly more temperature variation than the other. The standard model predicts the sky should look statistically identical in all directions. It does not quite. There is also the axis of evil, named somewhat humorously by the cosmologist who noticed it. This is a subtle alignment in the largest temperature patterns of the cosmic microwave background, where certain features line up with the plane of our solar system more closely than they should if the universe truly has no preferred direction. The alignment is unexpected, whether it is a measurement artifact, a foreground effect from within our own galaxy, or something physically real about the universe's large-scale structure is still debated. These anomalies, taken individually, can each be dismissed. Taken together, they paint a picture of a cosmic microwave background that has just slightly too many surprises for pure chance to carry comfortably. One physicist who has spent years studying these patterns is Roger Penrose, who proposed conformal cyclic cosmology specifically because he thought the cosmic microwave background might contain information from before our universe began. In his model, the circular temperature anomalies he identified in the data are not random. They are the afterglow of events that happened in a previous universe, pressed into the fabric of our own. His claims have been challenged by other scientists who argue the patterns he identified are consistent with noise. The debate is unresolved. What is clear is that the cosmic microwave background rewards careful study in a way that keeps producing surprises. It is not a static relic. It is an active data source, still yielding new information decades after its discovery. And the most unsettling possibility hidden in its patterns points towards something that overturns the most basic assumption in all of cosmology, that the universe had a beginning. What if the Big Bang was not the beginning? Standard cosmology teaches that the universe began roughly 13.8 billion years ago from a state of extreme density and temperature, expanded outward, and has been growing and cooling ever since. Everything that exists, every particle, every force, every dimension of space and time emerged from that initial moment. Before it, the question of what existed has no answer, because time itself began with the expansion. That is the standard model. It is supported by enormous amounts of evidence, and a small group of serious physicists thinks it is incomplete. Roger Penrose, one of the most decorated mathematical physicists of the past century, developed an alternative framework called conformal cyclic cosmology. The idea is that our universe is one chapter in an endless series of universes, each one born from the death of the previous one. The framework begins with an observation about the far future of our universe. As stars exhaust their fuel and die, as galaxies spread apart due to dark energy, as even black holes eventually evaporate through a quantum process called Hawking radiation, the universe approaches a state that is almost completely empty and cold. In that final state, nearly all massive particles are gone. Photons and gravitons, which have no mass, are all that remain. Here is where Penrose's mathematics becomes strange. In a universe with no massive particles, time and space lose their standard meaning. The equations that govern massless particles are conformally invariant, meaning they have no natural sense of scale. A very cold, very large, empty universe, and a very hot, very small, dense universe look mathematically equivalent when described only in terms of massless particle interactions. Penrose proposes that when our universe reaches that cold, empty state, it undergoes a mathematical transformation that is equivalent to a new Big Bang. The end of one universe and the beginning of the next are the same event, described from different sides of a mathematical boundary. Each cycle is called an aeon. Our universe is one aeon in an infinite sequence. The physical implication is striking. If massive black holes from the previous aeon collided and merged in the eon before ours, those collisions would have released enormous bursts of gravitational waves. As that previous universe transitioned into our Big Bang, those gravitational wave bursts would have left faint circular ring patterns in the energy distribution of our early universe. Those rings would show up as subtle circular features in the cosmic microwave background, rings of slightly different temperature pressed into the sky. Penrose and his collaborators have looked for these rings. They claim to have found patterns consistent with them in the Planck satellite data. Other researchers examined the same data and disagreed. They argued that the patterns were consistent with random statistical noise and did not require a cyclic explanation. The debate remains open, but the framework itself is mathematically rigorous and makes testable predictions, which puts it in a different category from speculation. A signal predating our universe would not be mystical, it would be physics, and the specific nature of that signal, what it would look like and where to find it, leads somewhere stranger still. If the universe before ours was real, it left evidence, and we might already be looking at it. In conformal cyclic cosmology, the bridge between one universe and the next is not a wall, it is a transformation. The dying universe, cold and almost empty, mathematically becomes the hot, dense beginning of the next one. Particles and structures from the previous eon do not survive in any ordinary sense. Their physical forms dissolve, but certain patterns, encoded in the gravitational radiation produced by the most extreme events, could persist through the transition. The most extreme events in any universe are the mergers of supermassive black holes. Black holes are the densest concentrations of mass that physics permits. When two supermassive black holes spiral into each other and merge, the collision sends gravitational waves outward in all directions, ripples in the fabric of space-time that travel at the speed of light. In the final moments of the previous aeon, as the last black holes in existence finally consumed their remaining material and began to evaporate, the gravitational radiation from those final collisions would have been the dominant energy signature of a dying universe. As that universe transitioned into our Big Bang, those gravitational wave patterns would have been imprinted onto the energy distribution of the newborn cosmos. The circular symmetry of the waves, radiating outward from each collision point, would create faint concentric rings in the temperature of the early plasma. When the plasma later cleared and the cosmic microwave background formed, those rings would have been pressed into it. This is what Penrose looked for. Not exotic new particles, not direct observations of another universe, but the geometric aftermath of gravitational waves from another aeon, recorded in the temperature map of our own sky. The scale of the rings he claimed to identify varied. Some were large, spanning many degrees of sky. Some were smaller. Their locations corresponded to no known structure in our own universe. No galaxy cluster, no massive nearby object that could create a temperature pattern through gravitational lensing or other conventional mechanisms. Critics argued the rings were pareidolia at a cosmic scale, the tendency of pattern-seeking brains to find shapes in noise. Statistical analyses produced conflicting conclusions. Some teams found the claimed rings consistent with simulations of a purely random cosmic microwave background. Others found hints of unusual circular correlation. The data available from existing satellites may simply be too noisy to resolve the question. The patterns, if real, are at the limits of what current instruments can extract from the microwave background maps. New generations of experiments aim for greater sensitivity. Future polarization maps of the cosmic microwave background, which measure not just temperature but the orientation of the light waves, may provide an entirely new layer of data to search. If the rings are there, better instruments will find them. If they are not there, conformal cyclic cosmology will need revision. Either answer is extraordinary, because a clean absence of the predicted rings would itself constrain what happened at the very beginning, and a detection would rewrite the history of the universe back to before time had a name. The mathematics behind this transition, though, involves a point where our physics breaks entirely. Somewhere in the temperature of the oldest light, the echoes of a collision that happened before our universe existed may be hiding. The image is almost impossible to hold in your mind. Two black holes, each containing the mass of billions of suns, products of an entire previous universe's worth of stellar evolution, slowly spiraling toward each other across the emptiness of a dying cosmos. In that previous eon, no new stars are forming. The galaxies have long since spread apart. The last light is fading. Space is cold and growing colder, vast and growing vaster. The black holes spiral together over millions of years. As they approach, space itself warps around them, curving and twisting with the geometry of extreme gravity. The final moments of the inspiral generate gravitational waves of enormous power, ripples spreading outward through the fabric of that dying universe at the speed of light, concentric rings of compressed and stretched space-time expanding in every direction. Then they merge. The combined mass collapses into a single entity. A burst of gravitational radiation fires outward from the event, the largest single release of energy in the history of that universe. And then, the universe that contained them ends. The transition happens. The mathematical boundary flips. That cold, empty cosmos becomes the hot, dense beginning of ours. In this framework, the gravitational radiation does not vanish. It gets folded into the energy of the new Big Bang. The pattern of those concentric rings, the signature of where each black hole collision happened in the previous aeon, gets pressed into the temperature of the newborn plasma that fills our universe. Hundreds of millions of years later, when our plasma clears and the cosmic microwave background forms, those rings are there, faint, stretched, overlapping with each other from dozens or hundreds of different collision events across the previous eon, but geometrically distinct from the random ripples produced by inflation. Detecting them requires looking at the microwave sky and asking a precise statistical question. Are there more circular rings of correlated temperature than a random distribution should produce? The answer to that question is not obvious from raw data. It requires careful analysis of the full sky temperature maps, searching for the specific pattern of concentric temperature correlations that gravitational waves would create. Penrose and his research partner Vahe Gurzadian published papers claiming exactly that pattern was detectable. Their analysis pointed to roughly 12 to 15 clear ring structures in the Planck mission data at positions that did not correspond to any known structure in our own universe. Responses from other physicists ranged from intrigued to skeptical. Several independent teams ran their own analyses of the same data and reached different conclusions. The methodology for identifying such rings in noisy data was itself debated. What makes this situation unusual in physics is that the disagreement is not about the theory, it is about the measurement. The framework is mathematically coherent. The question is purely observational. more precise data could settle it. And more precise data is being built right now. But before any measurement can be interpreted, there is a deeper problem sitting at the very first moment of the universe. A place where the mathematics of physics does not just produce strange answers. It stops producing answers at all. At the moment of the Big Bang, the universe hit a wall in our equations. Every scientific description of the universe depends on two frameworks. The general theory of relativity describes how gravity works, how mass curves space and time, how large objects attract each other, and how the fabric of the cosmos expands. Quantum mechanics describes how particles and energy behave at the smallest scales, where probability rules, where particles can exist in multiple states at once, and where measurement changes the thing being measured. Both frameworks are extraordinarily successful. General relativity predicted black holes, the expansion of the universe, and the bending of light around massive objects, all confirmed by observation. Quantum mechanics underlies every semiconductor, every laser, every chemical reaction understood at the molecular level. Between them, they describe essentially all of known physics. They are fundamentally incompatible with each other. At normal scales, this incompatibility does not matter. Gravity is too weak to affect quantum calculations meaningfully, and quantum effects are too small to disrupt gravitational ones. The two frameworks operate in separate domains without conflicting. Go back far enough toward the beginning, though, and the domains collide. At a point called the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, the universe was so small and so dense that both quantum effects and gravitational effects were simultaneously important. At that scale, you cannot calculate one without the other, and when physicists try to combine the equations, they get infinities, division by zero, numbers that have no physical meaning. The singularity, the single point of infinite density and zero volume at the very start, is a place where the laws of physics, as currently written, produce no valid answer. The equations break. General relativity predicts its own failure there. The universe as physics describes it simply did not exist before that point, at least not in any way the current mathematics can capture. This is called the initial singularity, and it is the most fundamental unsolved problem in theoretical physics. Several approaches have been developed to try to bridge the gap. String theory proposes that particles are not points, but tiny vibrating strings of energy, and in string theory, the singularity is replaced by a minimum size below which space cannot be compressed further. Loop quantum gravity proposes that space-time itself is made of discrete units, like pixels, and the singularity dissolves into a dense but finite state. In loop quantum gravity, the universe does not begin from nothing, it bounces. Before the Big Bang was a big crunch, a previous universe collapsing inward until it hit the minimum quantum scale of space-time, then rebounding explosively outward as our universe. This is called the bouncing universe model, and it is a different path to the same destination as conformal cyclic cosmology, a universe with a before. What happened in that before is where the story gets deeply strange. If there was a universe before ours, did anything make it through? The question sounds simple. The physics behind it is one of the most contentious debates in modern science, and it connects two ideas that normally live in entirely different corners of physics: the nature of information and the structure of black holes. In physics, information is a precise concept. It refers to the complete description of a physical system. Every particle, every position, every velocity, every quantum state. The laws of physics, as currently understood, are reversible. Run any physical process forward in time, then run it backward, and the information is conserved throughout. Nothing is truly lost. The future completely determines the past, and the past completely determines the future, at least in principle. Stephen Hawking showed in the 1970s that black holes emit radiation over enormous timescales. A black hole slowly loses mass through this radiation and eventually evaporates completely. The problem he identified was that the radiation appeared to be entirely random, carrying no information about what fell into the black hole. If a library fell into a black hole and the black hole then evaporated, the library's information would be gone forever. That would violate the conservation of information, one of the deepest principles in physics. Physicists argued about this for decades. Hawking eventually conceded that the information is preserved, though the mechanism by which it escapes the black hole remains deeply unclear. This is the black hole information paradox, and its resolution is still incomplete. Now apply this to the beginning of the universe. If our universe began from a singularity, all information from any previous state was presumably compressed into that point and then re-expanded in our Big Bang. The question is whether that compression and expansion preserved any of the original information in a usable form, or whether the Big Bang was a reset, wiping the slate clean. In the standard model, the Big Bang erases everything before it. The inflaton field that drove inflation would have thermalized the universe so completely that no ordered information from a previous state could survive. The universe we observe began fresh. In conformal cyclic cosmology, the transition preserves certain geometric patterns, specifically the large-scale gravitational wave signatures. The rest of the information is lost, but those specific patterns survive because conformal geometry is preserved across the boundary. In the bouncing universe model from loop quantum gravity, more information potentially survives the bounce. The compression is extreme but finite, and a finite compression, in principle, allows some structure to persist. What this means for the search is concrete. If the Big Bang erased everything, the cosmic microwave background is a fresh slate from our own universe only, and any signal it contains is from our aeon exclusively. If information survived from a prior state, then specific features in the microwave background or in the distribution of matter could carry that signal. The cold spot might be noise. The circular rings Penrose identified might be noise, or they might be the only message that ever survived the death of a universe. Before the Big Bang, there may have been a big crunch. The standard picture gives the universe a sharp starting point. One moment, nothing. The next, an explosive expansion from a state of extreme density. Physics begins. Time begins. The universe expands and cools toward the present day. The bouncing universe model replaces that sharp starting point with a smooth transition. Instead of a beginning from nothing, the universe has always existed, cycling through phases of expansion and contraction. The cosmos expands for billions of years, then gravity and other forces eventually reverse the expansion, drawing everything back together in a slow but accelerating collapse. The universe contracts toward extreme density, but instead of compressing to a true singularity, it hits a quantum limit, a minimum size that space-time itself cannot be squeezed below. At that point, the collapse rebounds. The universe bounces outward again. What we call the Big Bang is the rebound from a previous universe's big crunch. The physics framework that most naturally supports this idea is loop quantum gravity, a theoretical approach that treats space-time as made of discrete units rather than a smooth continuum. Just as matter cannot be divided below the scale of individual atoms, space and time cannot be divided below a minimum scale called the Planck length. When a collapsing universe reaches this scale, the quantum geometry of space-time resists further compression and the collapse reverses. In simulations based on loop quantum gravity, the bounce happens smoothly. There is no singularity, no breakdown of the equations. The collapsing universe transitions directly into an expanding one, and certain properties carry across. The large-scale geometry of the pre-bounce universe can influence the geometry of the post-bounce one. This has an observable consequence. If our universe bounced from a previous contraction, the primordial gravitational waves produced during the bounce would carry information about the pre-bounce state. Those gravitational waves would have influenced the plasma era of our universe, leaving subtle signatures in the polarization of the cosmic microwave background, orientations of the light waves that reveal something about the conditions at the very start. Several upcoming experiments are designed to measure exactly this polarization signal The challenge is separating the signal generated by inflation, which produces its own gravitational wave signature, from any signal generated by a bounce. The two look somewhat similar, but they have predicted differences in the specific pattern of polarization across different scales. If the data matches the bounce prediction better than the inflation prediction, cosmology faces a fundamental shift. There is a further implication that makes the bouncing model especially strange to sit with. If the cycle has been running forever, with no first bounce and no last bounce, then the universe has existed for an infinite amount of time. There is no original creation. There is no first moment. The universe has always been, cycling through states of expansion and contraction, like a cosmic heartbeat with no beginning. That idea does not resolve the mystery at the beginning of everything. It dissolves it entirely. And dissolving the beginning creates a new problem. What shaped the universe that contracted into our bounce? And what shaped the one before that? The map of the hydrogen signal does not look quite the way the models predict. Scientists studying the 21-centimeter hydrogen line, the faint radio emission from neutral hydrogen gas during the Dark Ages, have found hints of something unexpected in their data. In 2018, a team using a small radio antenna array in the Western Australian desert reported a detection of the hydrogen signal from the Dark Ages. The detection itself was remarkable, the first potential measurement of radiation from the period before the first stars. But the signal was twice as strong as any standard model calculation predicted. The excess absorption meant the hydrogen gas during the Dark Ages was colder than expected, colder by a significant margin. The standard model allows for the gas to cool as the universe expands, but only to a certain temperature set by the cosmic microwave background radiation. The gas cannot cool below the temperature of the background radiation because the radiation keeps heating it. For the hydrogen to be colder than the background radiation, something else would have to be removing energy from the gas, something that interactions with normal matter could not explain. One proposal came quickly. A team of theorists suggested that a new type of dark matter particle, one that can interact weakly with ordinary matter through a long-range force, could drain energy from the hydrogen gas. If dark matter and the hydrogen gas exchanged tiny amounts of energy, with the dark matter acting as a heat sink, the hydrogen could cool below the temperature predicted by standard physics. This would require dark matter to have properties different from the most common theoretical models, which assume dark matter interacts only through gravity. A small interaction with ordinary matter, tiny but not zero, would have profound implications for what dark matter actually is. Some theorists pushed further. If the bouncing universe model is correct, the pre-bounce universe would have contained its own distribution of matter and energy. The bounce would have mixed and redistributed that material as it transitioned into our expanding universe. Certain dark matter distributions produced by the pre-bounce state would have left anomalous density patterns in the early hydrogen gas, patterns that would show up as unexpected features in the 21-centimeter signal. The Western Australia detection has been disputed. Other teams have not confirmed it at the same significance. The antenna used was simple, and the foreground removal was difficult. The team themselves noted that systematic errors could explain the excess, but the number was twice the prediction, and twice is not a small discrepancy. If future, more sensitive observations confirm the excess absorption and rule out instrumental causes, the standard model of cosmology will face a genuine crisis. An excess that large requires new physics. The options on the table include new dark matter interactions, modifications to the standard cosmological model, or, for the theorists willing to go there, evidence of conditions set before our Big Bang. The instrument capable of testing this cleanly is not yet built. It may need to be on the moon. What comes next in the search for these signals involves hardware that does not yet exist, built to hunt for things at the edge of what physics says can be known. The instruments that will answer these questions are being designed right now. The current generation of cosmic microwave background experiments has been extraordinary. The Planck satellite mapped the full sky in microwave frequencies with enough precision to measure temperature differences smaller than 100,000th of a degree. It gave cosmologists a detailed picture of the universe at 380,000 years old and produced the most precise measurements ever made of the fundamental parameters of cosmology. It was not enough. The features that Penrose identified in the Planck data are at or below the noise floor of the instrument. The polarization signal that bouncing universe models predict is fainter than what Planck could reliably measure. The dark matter anomalies in the hydrogen signal require radio telescopes with sensitivity far beyond what current arrays can deliver. The next generation of experiments targets all of these gaps simultaneously. The Simons Observatory in Chile, currently being assembled at an altitude of nearly 17,000 feet in the Atacama Desert, is designed to measure the polarization of the cosmic microwave background with 10 times the sensitivity of Planck. It will map the full southern sky in multiple frequency bands, looking specifically for the patterns in polarization that gravitational waves from the earliest moments would produce. If inflation happened, its gravitational wave signature should appear. If a bounce happened instead, a different signature should appear. The data will distinguish between them. Following the Simons Observatory, the CMB Stage 4 project plans to deploy even larger arrays across both the Atacama and the South Pole, combining the two sites into a single coordinated observation campaign covering nearly the full sky. Stage 4 aims to push sensitivity to the point where either a clear detection of primordial gravitational waves or a definitive upper limit is achieved. Either result rewrites the opening chapter of cosmic history. For the hydrogen signal from the Dark Ages, the Square Kilometre Array is the primary vehicle. Being built across South Africa and Australia, it will combine thousands of antenna elements into a collecting area equivalent to a square kilometre of telescope surface. At that sensitivity, the 21-centimetre signal from the Dark Ages should be detectable even at the low frequencies where it sits after billions of years of cosmological stretching. The Square Kilometre Array will produce maps of neutral hydrogen across vast stretches of cosmic time, tracing the evolution of gas from the Dark Ages through the epoch of reionization, building the first three-dimensional picture of how the universe transitioned from darkness to light. And above all of it, waiting for the moment when the technology, funding, and robotic construction capability align, the Lunar Farside Array remains the ultimate instrument. Shielded from all terrestrial interference, cooled by the lunar night, spanning potentially dozens of miles of antenna elements across the crater-pocked surface, it could push the hydrogen signal detection back further than any Earth-based instrument can reach. What those instruments find may force a rewrite of the opening chapter of everything. The James Webb Space Telescope was supposed to confirm the standard model. Instead, it complicated it. Launched in December of 2021 and reaching its observing position about 1 million miles from Earth, Webb was designed to see further back in time than any telescope before it. Its mirror spans 21 feet across, made of 18 hexagonal gold-coated segments working together as a single surface. It observes primarily in infrared light, which allows it to see through the dust clouds that hide star-forming regions and to detect light from the earliest galaxies that has been stretched into infrared wavelengths by billions of years of cosmic expansion. Within its first year of observations, Webb began returning images of galaxies at distances no telescope had reached before. Some of these galaxies appeared to exist at just 300 million years after the Big Bang, well before the point where the standard model predicted large, well-formed galaxies should exist. The standard model of galaxy formation, called lambda CDM, predicts that galaxies build up gradually. Small clumps of dark matter and gas merge over hundreds of millions of years, growing into progressively larger structures. The first large, well-organized galaxies should take over 1 billion years to form from the primordial gas clouds. Webb found them at 300 million years, fully formed, massive, containing stars that had already been through generations of formation and explosion. The discrepancy was significant enough that some researchers initially questioned whether the distance measurements were correct. Distance measurement in cosmology relies on spectral redshift, the stretching of light wavelengths by cosmic expansion. Webb's spectroscopic measurements confirmed the redshifts. The galaxies were where they appeared to be. Explanations multiplied. Some theorists proposed that the first stars formed more efficiently than models assumed, producing more ultraviolet light per unit of mass and driving reionization faster. Others suggested that early black holes grew faster than expected, providing gravitational seeds around which galaxies could assemble more rapidly. A smaller group proposed that something fundamental in the standard model was wrong, that dark energy, or the early expansion rate, had been modeled incorrectly, and that the universe had more time or more energy to build structure than current cosmology allows. The Hubble tension, a pre-existing disagreement about the current expansion rate of the universe measured by different methods, was already pointing at a possible crack in the standard model before Webb launched. Webb's early galaxy discoveries added another crack. None of these cracks have broken the model yet. The standard picture of the Big Bang, followed by inflation, followed by gradual structure formation, still describes the vast majority of what we observe. But the model is being stress-tested by data in a way it has not been before, and the pressure on the model is building. Imagine the readout. A signal arrives from a direction in the sky. The frequency puts it at a time before recombination, before the cosmic microwave background, before any light could have traveled freely in our universe. The detectors confirm it is real. Multiple instruments, in different locations, on different continents, record the same signal. There is no source in our universe that should produce it. This scenario is theoretical right now. No such signal has been definitively confirmed. But physicists take the possibility seriously enough that they have written papers on what the detection protocol would look like, how to rule out instrumental artifacts, foreground contamination, and known astrophysical sources before accepting that something genuinely anomalous has been observed. The first response would be systematic elimination. Scientists would search for every possible conventional explanation, every terrestrial source, every solar system object, every known astrophysical process that could mimic the signal. This process takes months or years. The history of astronomy includes many mysterious signals that eventually turned out to have mundane explanations. Pulsars, the rapidly spinning neutron stars that emit precise radio pulses, were briefly considered as possible evidence of extraterrestrial communication before their natural origin was understood. If conventional explanations fail, the signal enters a different category. It becomes a genuine anomaly, an observation that the current best model of the universe cannot account for. At that point, the scientific community faces a choice between three options. The first is that the measurement is wrong, that some subtle systematic error is producing a false signal in a way that resists easy identification. This is always the most likely initial explanation for any extraordinary claim. The second is that the signal has a conventional source that has not yet been identified, a new type of astrophysical object or process operating within our universe that produces radiation at unexpected energies and frequencies. The third is that the signal carries information from outside the standard model entirely, from a pre-Big Bang state, a different cosmological aeon, or a structure in the physics of space-time that current theory does not include. The third option is the most extraordinary and requires the most extraordinary evidence. But physics has encountered exactly this situation before. In 1998, observations of distant supernovae returned a result that every reasonable cosmologist at the time would have called impossible. The expansion of the universe was speeding up. The force driving that acceleration, dark energy, is still not understood at a fundamental level. It was accepted because the evidence from independent lines of observation was overwhelming. An impossible signal, confirmed by multiple instruments and stripped of every conventional explanation, would enter physics the same way, with resistance, with scrutiny, and eventually, if the evidence held, with acceptance. What that acceptance would mean for humanity's understanding of its own origin is something no equation has fully worked out yet. If the universe had a before almost every question humanity has ever asked gets harder, the standard model of cosmology offers a kind of psychological shelter. The Big Bang was the beginning. Before it, nothing existed. The word before does not even apply because time itself began with the expansion. There is no prior state to ask about, no deeper origin to search for. The universe simply begins, and questions about what caused it or what preceded it are category errors. The wrong kind of question applied to a moment outside the framework of cause and effect. That shelter disappears the moment a previous aeon becomes real. If our universe bounced from a previous one, or emerged from the death of a previous one, or shares a mathematical boundary with one, then the chain of causation extends backward beyond the Big Bang. Our universe had causes. Those causes existed in a prior state. That prior state had its own physics, its own history, its own beginning, or its own eternal past. The question of ultimate origin does not disappear. It steps back one level and asks the same thing louder. This is not a problem unique to cyclic cosmology. String theory landscapes propose that our universe is one of an enormous number of possible universes, each with slightly different physical constants, each inflating and cooling into a different configuration of matter and forces. In that picture, our universe is also one instance among many, and the chain of causation again extends beyond our own Big Bang. What changes is the relationship between physics and meaning. Humanity has oriented its deepest questions around origin. Every culture, every philosophical tradition, every religion has some account of how things began. Physics entered this conversation with the Big Bang and offered a scientific origin, a hot, dense state that expanded into the cosmos we observe. That account is compelling and well supported. A cyclic universe removes the origin entirely. There is no first universe. There is no first moment. The process has always been running. Time is not a line with a start, but a cycle with no beginning, or an infinite sequence stretching backward without limit. For science, this is an extraordinary opportunity. A universe with a before is a universe with more to study. The signals from prior aeons, if detectable, extend the domain of observational physics beyond what anyone thought possible a generation ago. For humanity as a whole, the implication is stranger. The universe is older than the universe. Our 13.8 billion years of history is one chapter in a book that has no first page. Every atom in your body passed through the Big Bang. Some theorists now suggest those atoms may carry quantum-scale imprints from conditions that existed before our Big Bang even happened. The matter you are made of could be, in a microscopic sense, older than the universe you live in. That idea has not been confirmed. The evidence is circumstantial and contested, but the fact that it can be asked as a physics question, grounded in mathematics, tested against data, is one of the most remarkable developments in the history of science. At the edge of everything we know, there is a wall. The cosmic microwave background sits at the outermost boundary of what light can ever show us. It formed 380,000 years into the history of our universe, and nothing that happened before it can be observed through any electromagnetic signal. The wall is physical. It is built into the nature of light itself, into the opacity of the early plasma, into the speed limit of the universe. For most of the 20th century, that wall was the end of the road. The 21st century opened a crack. Gravitational waves do not interact with plasma. They pass through the opaque early universe the way neutrinos pass through solid rock. A gravitational wave produced at the moment of the Big Bang, or during inflation, or during a pre-Big Bang bounce, would travel through the plasma era unimpeded and arrive today with information about the conditions at the very start. Detecting the primordial gravitational wave background is the central goal of the next generation of cosmic microwave background polarization experiments. If inflation happened as predicted, those experiments will detect a specific pattern. If a bounce happened, the pattern will differ. If neither model is exactly right, the data will point toward what is missing. Relic neutrinos are the second crack. if detectors advanced enough to catch them are ever built. They carry information from 1 second after the start, far closer to the beginning than any electromagnetic signal can reach. The physics required to build such a detector sits just beyond current engineering. The motivation to reach it has never been stronger. And then there is the possibility of the signal itself, the one that opened this story. A feature in the cosmic microwave background, a ring, a cold spot, a polarization asymmetry that has no explanation within our own universe's history. Something pressed into the fabric of the cosmos from a time or a place that our standard model does not include. These searches are active. They are funded. Scientists are building the instruments right now. The honest answer to whether we can see beyond our own beginning is that we are trying, harder than we have ever tried before, with better tools than we have ever had, and we do not yet know what we will find. What we know is this: the universe is not silent. It is broadcasting its own history in every direction, at every frequency, in particles that pass through everything and in light that has traveled since before Earth existed. The oldest signal ever detected is still arriving. It left its source 13 billion years ago, and it reaches us every second, carrying a map of the infant cosmos. Somewhere in that map may be the fingerprint of something older. The search for a signal that predates the universe is the search for the deepest answer physics can attempt. Whether the answer is that our universe is the first and only, or one link in an infinite chain, or something no model has yet imagined, it waits in the data, and the data keeps coming.